Thanks for the introduction. So the work I'll talk to you about today is joint work with Manuel Blum and Anupam Datta, who are my co-advisors at CMU, as well as Santosh Vimpala, who's at Georgia Tech. So start off by motivating the problem. Let's look at a common problem that we all face, password management. So you're an internet user. You have lots of different accounts online. Each of these accounts requires you to create a password. So the question is, what strategy should the user follow to create and remember all of his different passwords? And typically, the user has two competing goals, security and usability. And usability means that he doesn't want to spend too much effort trying to remember all of his passwords. And security means that he doesn't want an adversary to hack into his accounts. So for example, let's suppose that the adversary is able to trick the user into giving away one of his passwords, maybe by creating a domain name called paypal.com and phishing for the user's password. One of the questions we might ask is whether or not the adversary can now crack into all of the user's other accounts. So for example, can the adversary break into any of the user's accounts on Amazon or his bank account, for example? So this is a problem that I've been thinking about for several years. And we can consider a number of different strategies that the user might follow. One strategy might be to pick one simple password and just reuse it everywhere. This strategy basically requires minimal user effort, but it also doesn't provide any meaningful security guarantees. Another approach might be to just suck it up, try to memorize completely random strings for every account that you have, and pick independent strong passwords. And this approach is highly secure, but in some of my other work, we've argued that this strategy is just impractical. No user could actually follow this strategy. So two of the strategies I've developed, one's called shared queues, and another's called human computable passwords. And I've been on the faculty job market, and I've talked a lot about this work. To avoid boring myself, I'm going to talk about human computable passwords today. So the basic idea is to develop a scheme for humans to actually compute their passwords in responses to random challenges that they'll be given. And the key technical insight here, I'll elaborate more in the talk, but we're going to build on interesting results on the hardness of random planted satisfiability problems. OK, so for the talk, I'm going to give you a quick 10-minute version because the actual scheme is very simple. And I want to make sure I describe the scheme, what tasks we require the user to do, and make sure that the simplicity doesn't get lost in all of the technical details. So I'll describe the scheme briefly, and then I'll go ahead and repeat the talk and actually fill in some more of the technical details about the scheme. OK, so human computable passwords. So we're developing a scheme in which passwords are computed by responding to public challenges. And I want to stress that the rules of the game is that all of these computations are computations that are done inside the user's head. So we're not relying on a trusted computer to do computations for us. We're actually relying on schemes that you can compute inside your head without assistance from a calculator or a trusted computer. Well, because we're relying on calculations that can be done inside our head, we really need to restrict the space of functions that we look at. In particular, we can only require people to do simple operations. We can't ask people to evaluate discrete logarithms in their head or do other fancy cryptographic operations. In fact, we're only going to use two simple operations, addition modulo 10. So if I give you two numbers like 9 and 6, you can tell me that the remainder mod 10 is 5. And I'm going to ask you to memorize a random mapping, either from characters to digits or from images to digits. And these are the only operations that we require a human to do. So our goal is to develop a scheme that's secure after many breaches. This means that even if the adversary's seen many examples of the user's passwords, let's say 100 examples, he still can't predict the next password. OK, so again, human computation is very restricted. Operations are performed in limited memory. So we have 7 plus or minus 2 chunks of information that we can keep in working memory at any given time. And we can only do simple operations. So I'm never going to give users two large numbers like this to add. The only operations we'll ask people to do are simple operations like this. OK, so to start off using our scheme, you memorize a random mapping from images to digits. So for example, here we have an image of a lightning bolt, and maybe the random mapping says that this image maps to the number 9. Maybe the image of the dog maps to the number 3, and maybe the image of the zebra trying to get away from the lion maps to the number 6. So to start off using the scheme, you memorize a random mapping. And in this case, we'll use n to denote the number of images. So for example, maybe n is 30 images. I was able to memorize a random mapping from 100 images to digits for even stronger security guarantees. OK, and I would argue that mnemonics can make this process easier. So for example, if your random mapping said that the image of the eagle should map to the number 4, you might tell the user to remember that the word eagle, or that the eagle has a gold beak, and that there's 4 letters in the word gold, 4 letters in the word beak. Similarly, if this image happened to map to the number 7, you might tell the user to trace out the number 7 underneath the eagle's beak. And yeah.
Sorry, just checking. When you're saying tell the user, do you mean you have a system that will suggest mnemonics?
Yeah, so essentially you generate, for every image, you pick a random number. And then for whatever random number you generate, you have a mnemonic that you show the user to help him remember that mapping. So if it happened to be 4, you'd show him this mnemonic. If it happened to be 7, you might show him this mnemonic. So yeah, in general, we would have a table of mnemonics. This table would be for every image, you would have 10 mnemonics. And whatever random mapping you generate, you have a mnemonic to show the user. Yeah. Mm-hmm. Yeah. So OK, this scheme we haven't conducted extensive user studies. I'm going to briefly talk about another scheme where we have done more extensive user studies. But this scheme we haven't done extensive user studies. So memorizing the random mapping is admittedly the most painful process of using this scheme. So it took me about 2 hours to memorize the mapping from 100 images to digits. And that was just kind of by practicing it over and over again. I will talk a little bit about how to remember it over time. So one of the nice features of this scheme is that once you've memorized the random mapping, you will actually be practicing that random mapping a lot to authenticate. So I'll show you some data later about how much practice people get. But we're conjecturing that the hardest part is actually memorizing the random mapping. But after you memorize it, you get so much practice that it's easier to remember it over extended duration of time, like 6 months. OK, so this is what the authentication experience would look like in this scheme. So to authenticate, you respond to a sequence of single-digit challenges. And in this case, a single-digit challenge is 14 images displayed on the screen as follows. So to respond, the user starts off with the first 2 images, adds them together. In this case, 9 plus 3 is 2 mod 10. You look up the second image in this table over here and add that image to the remaining 2 images. So in this case, 7 plus 4 plus 5 is 6 mod 10. And so if you're logging in, the first digit in your password would be 6. Type in 6, and you get another single-digit challenge. You solve this single-digit challenge in exactly the same way. Add the first 2 images, look up an image from the table, add it to the remaining 2 images, and enter in your digit. You repeat several times to strengthen your password. OK, so yeah.
That's just equivalent to just adding all 4.
To adding all 4?
Right.
Well, it's appending each. Yeah, so the length of the password grows over time.
But this mapping on the bottom right those numbers are displayed?
Yeah, these numbers are displayed. So this is just a lookup table. So here we add these two images. That gives us an index. So you look up the second image in this table.
But the image is not the same.
The image is not the image is not the same from challenge to challenge. Yeah, and the reason for this lookup step here is to break linearity. If we just added all of these digits together, then we're getting linear constraints, and you could use Gaussian elimination to solve. So this lookup process here actually breaks linearity, and I'll talk about that a little bit more later. Okay. So I'll talk a little bit more in detail about usability, but briefly, it takes me about 7.5 seconds per digit. So the scheme does require more user effort. That's about 30 seconds for a 4-digit password and about 75 seconds for a 10-digit password. And memorizing the secret mapping is the most challenging aspect of using the scheme. It took me about 2.5 hours to memorize mapping from 100 images to digits. It's faster if you want to memorize a mapping from, say, 30 images to digits. The nice thing is that this is a one-time cost, and I'll make that argument later in the talk. Okay. Actually, I'm going to make that argument right now. Okay. In other work, we developed a model to predict how many extra rehearsals a human would need to remember a secret over time. So the basic idea is to remember a secret, we need rehearsal. We need practice. And if we don't get practice, it's likely that we'll forget that secret. So there's literature in the cognitive psychology domain about spaced repetition and how frequently someone would need to rehearse a random secret to ensure that he remembers that secret over time. And roughly, you start off with shorter intervals, and then the intervals grow over time. So at first, after you've memorized a secret, you'll need to rehearse that secret pretty quickly, say in the first 12 hours after you've memorized the secret. But then after you've got more repetitions, these intervals grow, and maybe after 10 repetitions, you can wait 60 days at a time before rehearsing it. One of the nice things is that in the scheme, to authenticate, you actually have to recall many pieces of your secret mapping. So to compute a 10-digit password, you need to actually recall the values of sigma for 50 different images. So in this case, you're getting lots of practice every time you log in at remembering different pieces of your secret mapping. So we can actually predict how many extra rehearsals beyond natural practice someone would need to actually be able to remember all of their secrets. And here this is a theoretical model, but we actually made these predictions. And so we introduced 4 types of users: an active user who authenticates fairly frequently to his accounts, and an infrequent user who is like grandma, maybe uses the computer once a year. So here we can make predictions about how many extra rehearsals the user would need to do after memorization. And we can see that if you memorize a mapping from 30 images to digits, essentially you don't have to do any extra rehearsals over your lifetime, which means that you're already getting enough practice to remember your secret mapping. If you want to memorize longer secret mapping from, say, 100 images to digits, then you are going to need to do a little bit of extra work. Yeah? So essentially, you have rehearsal requirements, which basically states that if you memorize a secret, you need to rehearse it once during the first 12 hours, then once more, say, during the next 18 hours after that, and then these intervals grow over time. So we can introduce profiles for the user, which basically specify how often does this user authenticate on average. So how often do you visit Google? Maybe once a day. How often do you visit Amazon? Maybe once a month. How often do you visit your bank account? Maybe once a month. And so every time you authenticate, you actually get some natural practice with the secrets that you've memorized. So then we essentially predict, okay, well, in this course of getting natural practice, do you actually get sufficient rehearsal to satisfy all of these constraints? And these numbers are the number of unsatisfied rehearsal constraints. So if a rehearsal constraint is unsatisfied, that means that you need an external program to send you a reminder, hey, you better look at this picture and try to remember what the image of the lightning bolt maps to. Otherwise, you haven't used that secret mapping in a while. Otherwise, you might forget it. So essentially, this is predicting how many reminders you would need to rehearse. Sorry, I omitted some of the details from this talk because this is work from my other paper. Any other questions about this slide? Okay. Well, I'll move on, and if you're interested, please ask me about it later. Okay. So what about security? Well, what we're able to prove is that any statistical algorithm needs to see at least n to the 1.5 random passwords before it can even approximately guess the secret mapping. So for example, here n might be 30 images, so you need 30 times square root of 30 example passwords to recover the secret mapping. So what do I mean by a statistical algorithm? Well, a statistical algorithm can be viewed as just a large tree. And at each node in this tree, you have a query function. So to traverse this tree, you draw a random challenge response pair. And you apply the query function to that challenge response pair. And the query function basically has a range of L. So the response indicates an edge to take in this tree. So maybe the query, you draw a random challenge response pair. Maybe the query tells you to traverse this edge. You draw another random challenge response pair. You identify a new edge to take. And eventually, you get down to a root in the tree, at which point you output a guess for the secret mapping. So what we're able to argue is that any such adaptive search tree needs to have depth at least m equals n to the 1.5. Otherwise, with high probability, the secret mapping that you output is going to be uncorrelated with the true secret mapping. Yeah.
The queries are chosen at random, or
No, the queries are chosen adaptively by the adversary. So the adversary fixes any tree like this. And then the way we traverse the tree is by drawing random challenge response pairs. So the adversary picks the tree. It can be, the tree is going to be exponentially large, in fact, but the adversary doesn't control the way the tree is traversed. The tree is traversed by drawing random challenge response pairs and applying whatever functions he gives to traverse the tree. Yeah?
So should we think of this tree as a phishing attack?
Think of each example that the adversary gets as a phishing attack, an example challenge response pair. And the adversary has some strategy. Think of this tree as being the adversary's strategy to utilize that information and try to predict your secret mapping. OK, so I said any statistical algorithm needs this many examples. Well, why is this significant? It's significant because most known algorithmic techniques for solving planet satisfiability problems can be simulated by statistical algorithms. So Feldman, Perkins, and Vimpala had a paper in which they showed that some spectral methods, local search, expectation maximization, some methods for convex optimization can all be simulated by a statistical algorithm. The one exception is Gaussian elimination. Did you have a question?
So, yeah, I want to ask how well does the simulation preserve the numbers of the problem?
Yeah, so the simulation requires L to be roughly n to the 1.5 to simulate efficiently. So basically, if you have a spectral algorithm that requires n to the 1.5 examples, you can simulate this by a statistical algorithm using the same number of examples. So Gaussian elimination is the exception, but we also proved that the adversary needs n to the 3 example challenge response pairs before he obtains enough linear constraints to actually solve the system and recover the secret mapping. And finally, we proved that forging passwords is equivalent to recovering the secret mapping. So any adversary that can forge passwords could also recover the secret mapping. So it suffices just to argue that it's hard to approximately recover the secret mapping. OK, so I'm going to skip this for now, because we'll talk about some of the technical tools later. So we do have a challenge to break this scheme. And in this challenge, we've basically published challenge response pairs. And the goal is, from these challenge response pairs, recover the secret mapping and predict some of the challenge passwords. So for example, in this part of the challenge, the goal is to guess one of the user's secret 10-digit passwords given 100 of the user's other 10-digit passwords. So this challenge, I presented it at Asia Crypt at Oakland, and so far no one's been able to solve the challenges. Manuel has offered $20 for people who can solve one of the challenges. So there is minimal monetary incentive. Okay, so that's the end of the short talk. I guess it took me a little bit longer than 10 minutes due to questions, but let me go on and repeat the talk, but fill in a little bit more technical details.
Quick question.
Yeah.
How often do you expect people to generate a new mapping?
So the basic goal, is that you never actually have to generate a new mapping.
Right, so this like 30 to the 1.5 is like 160?
Right.
Something like that. So
Right.
presumably I might authenticate with my bank or something, you know, maybe that many times a year.
Right.
So
Right.
do I need to be like rekeying every couple months? Or?
Well, so basically, it's secure as long as the adversary hasn't seen that many examples. So once the adversary's seen more than that number of examples, then the scheme is broken. So yeah, if you use n equals 30, then it might be necessary to rememorize your secret mapping every now and then. If you memorize secret mapping from, say, 100 images to digits, then that's a lot more challenge response pairs that the adversary needs to see. So yeah, there's some trade-off between the amount of memorization work you're willing to put in at the start and the number of challenge response pairs that the adversary needs to see. So it really depends on how concerned you are about security. But basically, if you don't think that the adversary can ever see, say, 1,000 challenge response pairs, then maybe you're safe. You don't ever have to change your underlying secret. Okay. So okay, back to review. We're looking at the problem of password management. How can a person create and remember lots of different passwords? So let's start off by considering two different strategies that a user might follow. So one strategy might be to reuse a strong password. So if you've read XKCD, this is your correct horse battery staple style password. So the idea is pick 4 random words, memorize them, and now every account that you go to, your password is correct horse battery staple. Okay. Another strategy you might follow is to pick 4 independent random words per account. So in this case, you go to Amazon, you pick 4 random words. You go to eBay, you pick 4 independent random words. And okay, so these are 2 strategies that the user might follow. Now let's look at security. So we'll think about security as a game between the user and the adversary. And to play this game, the adversary gets to start off by maybe phishing 1 or 2 of the user's accounts. And we'll say that a scheme is secure if the adversary is unable to compromise any of the user's remaining accounts. So in this case, if you reuse the same password, then you're not secure under any of these attack scenarios. After the adversary's seen 1 of your passwords, he learns all of your other passwords. If you pick independent passwords, then you're secure under all of these scenarios. After the adversary's seen several of your passwords, he doesn't learn any information about any of your other passwords. The problem, though, is that it's too hard to remember completely independent random passwords. Part of the challenge is that many people have accounts that they visit, say, once a year. And if you've memorized a random password that's uncorrelated with any other password that you've memorized, after a year of not practicing, you're almost guaranteed to forget that password. So people are going to struggle to remember passwords under this scheme. So we have one scheme that's secure but unusable, one scheme that's usable but highly insecure. So the question is whether or not we can split the difference. Okay. So let me talk briefly about some previous work. Human computable passwords is only one scheme that we've developed. I want to tell you briefly about another password management scheme that we've developed that involves memorizing randomly generated person action object stories. So for example, imagine LeBron James standing on the bridge kicking a poor penguin. So if the user's memorized several of these stories, in fact, if you can memorize 7 of these stories, then that's already enough information to generate 75 unique passwords. And so the way the authentication process works in this scheme is we divide the person action object stories into two parts, a public key and a private secret. And when you authenticate, when you visit a website like paypal.com, you're prompted with a number of challenges. So for example, LeBron James on the bridge, maybe my advisor Manuel Blum on the hanging tent, maybe Anupam Datta with the Terracotta Warriors. And the response to these challenges is just formed by appending the corresponding actions and objects. So in this case, kicking penguin, torturing lion, kissing a piranha, etc. Similarly, when you go to another website like Amazon, you're prompted with a different set of challenges. And the key idea is to use combinatorial designs to ensure that every pair of accounts has at most gamma secrets in common. So notice here that when the user logs into paypal.com and when the user logs into amazon.com, this challenge involving LeBron James on the bridge is the same in both instances. And there's two advantages of doing this. One of the advantages is that you have fewer stories to remember. But the bigger advantage is actually that you get more practice for each of the stories that you've memorized. So here, the user gets to practice his story involving LeBron James on the bridge every time he logs into PayPal and every time he logs into Amazon.com. OK. So we developed a couple variations of this scheme using different combinatorial designs, where the combinatorial design essentially specifies how much sharing is allowable. So how much information is one account allowed to leak about another account. So if you want to use higher security versions of these combinatorial designs, it involves memorizing more person action object stories. If you want less secure versions of the combinatorial designs, you can really minimize the number of person action object stories you need to memorize. In fact, seven stories is already enough to generate 75 unique passwords. So there's moderately strong security guarantees that we get from these schemes. So for example, if an adversary's seen any two of your passwords, he's not going to be able to predict any of your other passwords if you use the shared queue scheme with the higher security parameters. If you use the shared queue scheme with these lower security parameters, meaning that there's a higher overlap between the challenges that two sites use, different passwords can be more similar. In this case, you're secure under this first attack scenario. So an adversary who's seen one of your passwords is not going to be able to compromise any of your other passwords. However, I'll point out that all of these security guarantees are limited. So once the adversary has seen several of your passwords, for example, an adversary who's seen 4 of your passwords is going to be able to learn all of your secrets and eventually start predicting all of your other passwords. Another area of related work is developing password managers. So password managers are software packages which you use to generate lots of passwords from one master password. So there's commercial applications like LastPass, 1Password. Stanford has their application called Password Hash. You go to it and you type in the URL, you type in a password, and then they generate a random string by applying some hashing algorithm. And this random string is your final password. So these schemes are nice in that they can generate lots of passwords from one master password. But the disadvantage is that they do require strong trust assumptions. If an adversary is ever able to phish you or shoulder surf you, then he's going to learn your master password, and he's able to compromise every account that you have. So unless your usage model looks like this, it's possible that someone with a hidden camera or someone just looking over your shoulder might learn your secret password. Or if any of the computational devices that you ever use to authenticate is infected with malware, it's possible that the adversary will learn your master password and break into your account. So here, I personally use my cell phone, my desktop computer, my laptop, sometimes computers at a public library, sometimes friends' laptops. If any of these devices is ever infected with malware, then the adversary would learn your master password and break into every account that you have. So the question is whether or not we can develop schemes with stronger security, and that's the goal of human computable passwords. So, well, why might this be useful? So here's a montage of some of the scary attacks that have been happening over the last few years. So there's a Russian group that's reportedly collected 1.2 billion passwords. There's been an increase in keyloggers to steal passwords by just monitoring keystrokes on users' laptops. More stories about the uptick in keyloggers. And of course, there's also famous security bugs like Heartbleed that potentially could leak master passwords when they were supposed to be encrypted, but due to implementation errors, an adversary was able to get around it. Okay, so back to our scheme, human computable passwords. So our goal is to develop a scheme that's secure after many breaches. So an adversary who's seen maybe 100 passwords can't learn any of your other passwords. So again, passwords are computed by responding to public challenges and will only require simple operations. So let's think a little bit more about human computation. So the rules of the game are that we're not allowing pen, paper, calculators, trusted computers. So the question is, what functions can we actually compute in our head? One of the limiting factors is that we have a small working memory. So we can keep about 7 plus or minus 2 chunks of information in our brain at any given point in time. And we also want to develop functions that are relatively quick to compute, meaning that you're not going to spend hours trying to compute each digit. So again, this is an example of a simple computation. This is not so much. Okay, again, the pre-computation in the scheme is memorizing a mapping from images to random digits. And there's mnemonics to help make this process easier. So let's formalize the goal of human computation a little bit. In particular, to formalize this, let's consider a small set of primitive operations. So for example, a primitive operation might be adding 2 digits mod 10, or given an image, recalling the secret value associated with this image. So we'll say a function f is ptm computable if there's a space m streaming algorithm to compute f using only t operations from the set of primitive operations. So in particular, the primitive operations we'll consider are addition. So input 2 digits, and the output is the addition mod 10. Also a recall operation where the input is an image and the output is the secret value of that image. And also a table lookup operation where the input is an index I. You're also given a table of 10 images, and the output is the corresponding image in that table. Okay, so our conjecture is that given a set of primitive operations that only includes these 3 operations, addition, recall, and table lookup, there's a small constant, gamma h, which we conjecture is about 1, such that any pt3 computable function can be evaluated by a human in t times gamma of h seconds. Yeah.
Sorry, can you give the definition of PT3?
Of PT3. So yeah. So P is the set of primitive operations. So a function that can be computed using only instructions from this set. T is the number of operations. So the number of operations from the set that the human's computing. And 3 is the memory requirement. So the amount of chunks that you're required to store in working memory at any given time. I found for myself that my constant is about 1. And I would conjecture that for members of this audience that similarly, gamma is about 1, maybe a little bit less, where you are members of computer science theory audiences. And let me actually show you a video of some kids doing similar computations.
Ready? Next. 2 9 6 1 5 8 9 3 4 7 2 1 3 8 5 7 3 6 4 9. That is 102 is the right answer. Next. 5 6 9 2 4 6 8 1 7 3 8 2 1 6 4 9 2 5 7 3. That is 98 is the right answer.
All right. Oh, we'll do one more.
20, 76, 37, 75, 53, 89, 62, 40, 14, 98, 61, 59, 34, 78, 90, 15, 86, 41, 23, 20. That is 1071 is the right answer.
Okay, so what do we learn from this video? Well, we learned that the value of my constant is way bigger than the value of the constant for these kids. So these kids could actually probably compute passwords in this scheme far faster than I'm personally able to do it. Yeah.
So those kids are great.
Yeah.
Is that your target audience, or is it the
Yeah.
person at the supermarket who can't even give me accurate change?
That's no. Yeah. That's yeah.
So the people I think are most at risk
Yeah.
are people who maybe can't add.
Yeah.
They can add. They can't do modular.
Yeah.
They can't do modular.
Yeah. That's
So I'm just.
Yeah.
I mean, it's fine if
Yeah.
your target audience is those kids and us.
right.
But I'm trying to understand where the.
Yeah, no, that's an excellent question. So what I would say is that for right now, the target audience for this particular scheme is people with a technical background or people like those kids who are able to do math in their heads. Ultimately, though, the goal is to design to move to developing schemes that your average person in the supermarket would be able to do. We're not there yet. But that's one of our goals, is to continue to simplify operations so that we can get a scheme that your typical person in the grocery market would actually be able to do it. But I'm not claiming that we're there yet. So right now, we're just presenting a scheme that is,
So I'm curious
yeah.
how you're going to get there. That is, if you are the typical person you measure your
Right.
algorithms by
Right,
and capabilities by, that seems a stretch for getting to
Right.
the ordinary person on the street. So
right.
what's your research plan in terms of coming to understand what operations
Yeah.
people can do?
Yeah, so some of the other work that we've been working on is involving simpler schemes where the operations involve memorizing randomly generated person action object stories. So the security guarantees of these schemes are weaker than the security guarantees of this scheme. But I would argue that that's a scheme that your average person out there could use. And we've been looking at maybe other primitive computation operations that people can do. It is a tough challenge, though, because you have to, given these operations, you actually have to show that people can do these operations, and then you actually have to argue that you can construct a secure scheme from these operations. So I'm not claiming to be there. We have some ideas about getting there using some other mnemonic tricks, but I'm not claiming we're there yet.
I guess I'm just
Yeah.
suggesting that you, rather than starting with what will work computationally,
Right.
rather you might start with what's the set of things that ordinary people can easily do,
Right.
and see how you
Yeah.
build on from that.
Yeah. So that's a different talk. So that's I guess that's more in the alley of the other paper I had on naturally rehearsing passwords, which I almost decided to give here, but I've given that talk like 6 times in the last 2 weeks, so I was a little bit bored of giving it. Okay. Let's see, where are we in terms of time? 12:18. Okay. All right. So let me briefly review the candidate scheme again. So we have a single-digit challenge, which is 14 images. Computing the response involves adding the first 2 images, looking up an item from the table, and adding it to the remaining 2 items. So in this case, the response is 6. And again, to authenticate, you solve several of these challenges. So to generate multiple passwords in this scheme, you would generate a random public challenge for every account that you have. And then your password for each account is formed by responding to those challenges. So I have challenges for Amazon. My password is computed by computing the responses to each of these random challenges. So in general, we're going to use K1 to be the number of addition operations before we have this table lookup. We'll use K2 to denote the number of images after the table lookup. So in this case, we're adding two images. K1 is equal to 2. We're adding 2 images, looking up the image below, and then adding that image to K2 other images from the table above. OK, so here's a formal view of the scheme that I just showed you. So we have a secret mapping, which is just a mapping from n objects to digits. We have K1 and K2. And a single digit challenge is just an ordered subset of size K equals K1 plus K2 plus 10. We need 10 images for the lookup table. So in the examples I was showing you, K was equal to 14, but we could adjust the scheme by changing the values of K1 and K2. And formally, the response to each digit is computed by applying this function to the corresponding secret values in a challenge. So given a challenge, we apply sigma to this challenge to get K1 plus K2 plus 10 secret digits. We apply this function, and that gives us the response, where the function basically sums up the last K2 digits and then adds 1 digit from the lookup table, where this index I here is computed by adding the first K1 items from the table, or from the challenge. OK. Theoretical usability analysis. This function is P 2K1 plus 2K2 plus 1, 3 human computable, which means that it can be computed by a streaming algorithm which requires 3 memory slots, primitive operations, just addition, recall, and table lookup. And we need 9 primitive operations to compute the functions that I was showing you, which was F22. So we would conjecture that this means that you can evaluate the function in under 9 seconds, where 9 is the number of primitive operations that you need to do to actually compute your password. So OK, this gives an authentication time of about 7.5 seconds per digit, about 30 seconds for a 4-digit password. And again, the main cost is memorizing the secret mapping. So as before, we have a theoretical model to predict the total amount of extra work that you would need to do to memorize your passwords. We talked about that earlier, so I'm going to skip it now. So what about security of the scheme? Well, we have both an empirical and a theoretical security analysis. The empirical security analysis was basically just taking a SAT solver, encoding the challenge response pairs as clauses in the SAT solver, and then letting it run to try to recover the secret mapping. And here we can see that when n is equal to 30 and we give 100, the SAT solver 100 challenge response pairs, the SAT solver was unable to recover the secret mapping in 2.5 days. When n is equal to 30 and we give it 10,000 challenge response pairs, it's able to find the secret mapping in 20 seconds. So there's a scale between the number of examples that the adversary gets to see and the amount of effort that he needs to spend cracking your password. When n is equal to 100, then even with 10,000 challenge response pairs, the SAT solver was unable to recover the secret mapping in 2.5 days of runtime. OK. So that's the empirical story. Let me tell you a little bit more about the theoretical story. Before I tell you about the security results formally, let me introduce some security parameters. So given a function f, we're going to use g of f to denote the minimum number of input variables that we would need to fix to make the function linear. So for example, if we have this function, which is just the sum of x1 plus x2 plus x3, we don't need to fix any variables. The function's already linear, so g of f is 0. If we have this other function, which is x1 if x2 if x3 plus x4 is even and x2 otherwise, then in this case we need to fix x3 and x4 so that the function becomes linear. So in this case, g of f is 2. And in our particular case, g of f is the minimum of k1 and 10. So in particular, we can make the function linear by fixing the first two input variables. And then once we fix those variables, then we've already fixed the index in the table, and the resulting sum is linear. Or we can make the function linear by just fixing every image in the lookup table, and then we get a linear function as a result. So the intuition, again, is that we add k1 values before we do the table lookup. If we fix these values, then the resulting function is linear. If we don't fix the values, then the function is not linear. So this result implies that our scheme can be broken by an adversary with order n to the k1 plus 1 random examples using Gaussian elimination. So if you draw enough random examples, then eventually you're going to see the same group of inputs in the first two spots, and then once you do, you can just apply Gaussian elimination and solve. Okay, our second security parameter is R of f, which is the minimum number of input variables that we need to fix to influence the output of f. So for example, let's suppose that f is again the sum x1 plus x2 plus x3. Well, in this case, if there exists a variable that we don't fix, let's say we don't fix x1, then the output of this function is still randomly distributed over the range 0 to 9. So in this case, R of f is 3. We need to fix all of our inputs before we influence the output of our function. In our particular case, we need to fix all K2 of the remaining challenge images, and we need to fix the image from our lookup table. So if we fix all of these images, if we fix the value of all these images, then we actually can influence the value of the function. So in this case, R of f is k2 plus 1. So what does this mean for security? Well, there's an attack that requires n to the R of f over 2 random examples and approximately recovers the secret mapping. And in fact, we can prove that any statistical algorithm needs to see at least this many examples to recover the secret mapping. So to formalize this intuition, we actually use Fourier analysis. So given a function q, which maps k digits to a real number, we can express this, this function as a linear combination of Fourier coefficients and Fourier basis functions. And in this case, the Fourier basis functions involve complex numbers, and the Fourier coefficients also involve complex numbers. In this talk, we're going to fix d to be 10 because people are used to doing operations in base 10 arithmetic. Okay, so formally, we can define our security parameter RF in terms of Fourier coefficients. So we can have an indicator function for the event that the response to a challenge is the number I. And in this case, our indicator function is 1 if that event occurs, 0 otherwise. And in this case, we can define R of f as follows. It's the minimum over all I and every possible Fourier coefficient of the Hamming weight of the Fourier coefficient of the smallest non-zero Fourier coefficient. And this is exactly equivalent to the intuitive example that I gave you before. Okay, and our goal is to prove that no adversary is able to find a secret mapping that's even epsilon correlated with the secret mapping that these are memorizes. Where here, epsilon correlated means that the Hamming distance is pretty much the same as the expected Hamming distance for random mapping. So if we pick two random mappings, sigma 1 and sigma 2, measure their Hamming distance, we expect that that Hamming distance is about 9/10. If it's a little bit smaller, say 9/10 minus epsilon, then we'll say that the secret mappings are epsilon correlated. So we're conjecturing that an adversary would need to see n to the minimum of r of f over 2, where r of f is our second security parameter, and g of f plus 1 challenge response pairs before it can find a secret mapping that's even epsilon correlated with the user's secret mapping. So in particular, for our particular functions, this would imply that the adversary needs m challenge response pairs where m is equal to the minimum of k1 plus 1 over 2 and k2 plus 1 minus some other epsilon prime. So in this case, we'll want to pick k1 and k2 so that these terms balance out. OK, what about password forgeability? So ultimately, the goal is, the adversary's goal is to forge the user's passwords. So given several random examples of the user's passwords, the adversary's goal is to break one of the user's other passwords. And the user wins this game if the adversary is not able to compromise any password he hasn't already seen in this game. So I should stress in this game that what the adversary gets is actually randomly generated challenge response pairs. We're not considering a security model where the adversary gets to pick adaptively which challenge response pairs he gets to see. So we're assuming that all of the challenges have been randomly generated, and the adversary only gets to see the responses to randomly generated challenges. OK, so we're conjecturing that it's hard to learn the secret mapping. One natural question is, could we forge passwords without actually learning the secret mapping? So in the theory of machine learning, it's oftentimes possible to learn a function if we aren't strict and we don't require proper learning. So it's natural to ask, well, could an adversary forge passwords without actually learning the user's secret mapping? So for example, DNF formulas, proper learning is NP hard, but they're pack learnable with linear threshold functions. In our case, we show that the answer is no. In fact, these two problems are roughly equivalent. So any probabilistic polynomial time algorithm that can forge passwords after seeing m challenge response pairs would be able to, we can transform this adversary into a probabilistic polynomial time algorithm that extracts secret mapping sigma prime that is correlated with the user's secret mapping with reasonably high probability. So roughly this theorem says that forging passwords is equivalent to learning the user's secret mapping. So in the rest of the talk, we're just going to argue that it's hard for the adversary to approximately learn the user's secret mapping. OK. Yeah, in general, this theorem generalizes to arbitrary functions as long as they follow some particular structure. For example, this function is equal to g of x1 through xk minus 1 plus xk mod d for some function g and for some base d. So in particular, this includes all of the functions that I've talked about, all of the example functions I've shown you, but it also could include other functions as well. So in particular, with our previous conjecture, this would imply that any probabilistic polynomial time algorithm needs at least n to the k1 plus 1 over 2 and k2 plus 1 examples before it can forge passwords with accuracy that's significantly better than just randomly guessing digits. OK. How much time do I have? 12:33.
It ends at 1.
OK. All right. Yeah, I'll maybe rush a little bit through some of the technical details, but stop me and ask questions if you're interested. OK, so the main result that we prove is that any statistical adversary needs at least m greater than or equal to this many challenge response pairs, where here n is the length of the secret mapping that the user's memorized, r is the security parameter of the function that the human's computing, and L is a parameter of the statistical algorithm. So yeah, and C is some constant that depends on some of these other parameters. OK, so basically, any statistical algorithm needs at least this many examples. Otherwise, he's not going to be able to find secret mapping that's even epsilon correlated with probability at least gamma. Okay. So just to review, statistical algorithm, this is any adaptive strategy that the adversary might use, where he picks a query function, gets a random challenge response pair, applies the query function to that challenge response pair to select one of L different results, and continues traversing his tree by selecting a new query function adaptively, drawing a new challenge response pair, and at each leaf of the tree, he has to output a guess for the secret mapping. So here, the depth of this tree is the number of challenge response pairs that's necessary to traverse through the tree. And again, our statistical algorithm says that, our result says that any statistical algorithm needs at least this many challenge response pairs. So here, L is the parameter of our statistical algorithm. So the statistical algorithm is allowed to ask queries that take a challenge response pair and map it to one of L different results. So here, this L parameter shows up in the final bound. So it's significant because Feldman, Perkinson, and Paula showed that a lot of these different algorithmic techniques for solving random planted satisfiability problems can be simulated efficiently by a statistical algorithm. So a few of these simulations do require us to set L to be n to the R of f over 2. Otherwise, we would need to draw more challenge response pairs to simulate the algorithms as a statistical algorithm. So a special case of our main theorem says that if we set L equals to n to the R of f over 2, then the statistical algorithm needs at least n to the R of f over 2 challenge response pairs to find a correlated secret mapping. So this is evidence that the best known algorithms are going to require n to the R of f over 2 random challenge response pairs before they can solve. Yeah?
So just a reminder, R of f is the Fourier coefficient, which is the smallest one?
Yeah, the easiest way to think of it intuitively as the minimum number of inputs to the function that you would need to fix to bias the result of that function. So a function is unbiased if you draw a random input and the probability of 0 through 9 is equally likely, 1/10. If you can fix some of those inputs and bias the function, then this is R of f, the minimum number of inputs that you need to fix. So yeah, it's also, in terms of Fourier analysis, the size of the minimum non-zero Fourier coefficient. Okay, so I'm going to give you a brief overview of this proof. So some of these slides are a bit denser than the rest of the talk. But here's a high-level outline of the proof. So we use this notion of discrimination norm, which says, on average, how much different would the answers to a query Q be if we picked a random challenge and a random response instead of picking a random challenge and then computing the true response? And Feldman, Perkinson, and Paula showed that if a search problem has a small discrimination norm, then this implies that the statistical algorithm needs a deep tree to actually solve this search problem. So what we do is we use Fourier analysis to express the discrimination norm as a low-degree function. And then we apply the generalized hypercontractivity theorem to actually bound the expected value of this low-degree function. So what do I mean by discrimination norm? Well, we'll start off with this slightly complicated looking expression down below, this delta function. And so delta takes query h and a secret mapping sigma. And this last term here is the expected value of our query function when we apply it to a random challenge response pair with a random answer instead of the true answer. So that's h applied to a random challenge with a randomly drawn response instead of the true response. And here this first term is h applied to the challenge with the actual true response to the challenge instead of a random response. So we have this delta function here, and then the discrimination norm is basically computed by taking a large set of secret mappings and looking at the maximum over all queries with norm 1 and taking the expected value over all secret mappings in this set of this delta function. So taking the maximum over all queries h with norm 1. and then the expected value taken over all secret mappings in this set. So the statistical dimension of a search problem is the largest integer, denoted by SDN, statistical dimension, such that, okay, there's two parameters here, kappa and eta. So eta here says that for all sigma, the set D sigma, which is the set of all secret mappings that are not epsilon correlated with our secret mapping, has to have size at least 1 minus eta times 10 to the n. So eta here specifies that, that this set D sigma has to be relatively large. And then we also want to say that for all subsets D prime, subsets of D sigma, where D prime is sufficiently large, larger than the size of D sigma divided by the statistical dimension, we have the discrimination norm is smaller than kappa. So that's a mouthful, but our goal is to show that the statistical dimension is large even when this kappa term, this discrimination norm, is small. Why is this relevant? Well, it's relevant because Feldman, Perkinson, and Paula showed that any statistical algorithm needs at least this many examples to solve a search problem. So D prime here is the statistical dimension. So we want D prime to be large. So this first term in the minimum is large. We also want kappa to be small. Otherwise, the second term in the minimum is going to be so that the second term in the minimum is large. So we want to balance kappa and D prime so that this term here is large. Okay, so what we prove is that indeed the statistical dimension is large even when kappa is small. So in particular, if we set kappa to be roughly 1 over n to the r of f over 2, and we set D prime, we pick D prime, the statistical dimension, to be larger than n, then we have this bound on the statistical dimension. So now the main theorem follows easily. If we set D prime equals n to the r of f, and kappa is equal to this term. So in particular, D prime is n to the r of f, so we have n to the r of f over here, and then we have n to the r of f down here, but n to the r of f over 2, but we have n to the r of f over 2 squared. So we get, we get n to the r of f in both cases. And so the main result then is that we need n to the r of f examples to actually find a secret mapping that's correlated with the secret mapping that the users memorized. Okay, so to analyze the discrimination norm, the main goal is to actually bound the value of this delta function. And to bound the value of this delta function, we use Fourier analysis to break up this delta function into the sum of small norm degree L functions. So in particular, B of L here is a degree L function. And degree L functions are functions that can be expressed as a sum of functions where each function depends on at most L variables. So we show that our delta function can be decomposed in this way, where it's the sum from L equals R of f to k. So basically, we don't have to rely on any values of L smaller than R of f. And the nice thing here is that BL is a degree L function with bounded with a small norm, and here it's divided by n to the L, by roughly n to the L. So we have sum of a bunch of terms, but we have this term n to the B of L over n to the L, where n to the L gets smaller as L is larger than R of f. So the dominating term here is actually just when we set L equal to R of f, and then we get B of L divided by n to the R of f. So the proof involves Fourier analysis and some algebraic manipulation. I'm not going to do it here, but if you're interested, see the paper. The general hypercontractivity theorem basically says if B is a degree L function, then the probability that the absolute value of this function is significantly greater than its norm is bounded by this term here, where the norm is defined in terms of the expected value of the function squared. Okay, so now by applying the hypercontractivity theorem, we get a bound on the absolute value of the function, and we can show that the absolute value of the function is smaller than the norm of the function divided by 10 to the L here. Okay, and finally putting it all together, we get bounds on the functions from our, we had broken up this delta function into a sum of BLs, and now we can bound the value of BL and show that it's roughly, the dominating term here is 1 over n to the L divided by 2. So this 1 over n to the L divided by 2 is the dominating term, and again here we're setting L equal to R of f. That's the biggest term here. So our final result is that we bound the discrimination norm, and it's roughly 1 over n to the R of f over 2. Okay, so sorry I had to kind of rush through that, but you can ask me questions about the analysis offline. So future challenges, one of the main challenges is developing schemes that even more people could use. So we talked about your user at the grocery market, what schemes could he actually do. Another challenge is improving response time. So there is a simple way to improve response time. One of these ways is by memorizing an additional map from words to from digits to words. And then the response to each challenge is no longer a digit. The response to each challenge is the corresponding word. So the advantage is that now you have to solve fewer challenges to compute each password. And actually, doing this extra step does give you an empirical security boost against SAT solvers. Other directions involves eliminating the semi-trust assumption. So we're using computers to store our challenges in the scheme. Another question is, could we just use URLs as the challenges for each account? So could we have a scheme that involves taking the URL and then applying some function to the URL and actually computing a password from the underlying URL? And another nice question is, what cryptographic protocols could a human execute in his head? So for example, could we develop secure bit commitment schemes that are secure even if you don't have access to a trusted computer? So even if the adversary can observe all your interactions, can we still develop bit commitment schemes that are secure? And another goal would be secure cryptography under constant surveillance. So what cryptographic operations could we achieve in a world where there's always cameras kind of pointed at your computer and anything you ever do is observed? We have some ideas that involve using our scheme with program obfuscation. And unfortunately, program obfuscation isn't yet at the point where it can be practically used. But with program obfuscation, actually, our scheme could already be used to do a lot of cryptographic operations that would be secure even in a constant surveillance world. So again, there's the challenge to break our scheme, and well, yeah, $20 prize to people who can break it. So it's not the world's largest prize for solving a challenge, but it's something. So thank you for listening, and I'll take any questions.
So I have one question about what exactly the system model is that justifies the assumption that the attacker doesn't get to choose challenges but can only eavesdrop on randomly chosen ones.
Right, so we're making a semi-trusted computer assumption, which basically means that we assume that the computer that you have preserves integrity of the data that you store, but it doesn't preserve confidentiality. So any data that you store on the computer is potentially something that the adversary will see, but we're assuming that the adversary doesn't have the ability to actively kind of maliciously change the data on your hard drive. So yeah, getting a scheme that's secure under the stronger security assumption where the adversary can actually kind of alter the challenges that you see. That's an even more difficult problem, but we don't claim to.
So the idea is you have this program running on your personal device.
Right.
That tells
right.
you how to generate the password to put into the.
Right. Yeah. So you have a program that kind of tells you go to a website and it tells you what challenge to solve, and you solve it. And the assumption is that the adversary can't kind of change those challenges that you'll see.
Is it for the same website? Do I always see the same challenge?
Yeah. Though you could think of an extension to the scheme where you have multiple kind of one-time passwords that you use for every website, and then in that case you would see different challenges for every website, or every time you authenticate to the same website.
That sort of addresses my earlier.
Okay. Yeah.
So if I only have one password for Bank of America, then I don't need to worry so much about.
Right.
About telling them.
Yeah. Yeah. So if you have the threat model that we were looking at that I used in the talk was basically an adversary who's compromised, say your Amazon account has already compromised that account, but we want to make sure that he doesn't compromise any of your other accounts. Now, if we want stronger security guarantees that an adversary who observes you type in your Amazon password still can't compromise your Amazon account, then we need to generate one-time passwords. And that's doable in this scheme, but I didn't, in the examples, I didn't use that.
Any other questions?
Yeah.
In my world, people asking for passwords have increased the length of the password
Mm-hmm.
and the class of the typed in information, like a subset of the computer keyboard.
Right.
Comma, punctuation marks and.
Right.
And so they're in fact requiring the password, people who
Mm-hmm.
password are requiring a kind of password.
Right. Right.
In your system,
Yeah, so I'll tell you a little bit about what I personally do to create and remember passwords. So I've personally used the other scheme primarily used the other scheme that I briefly mentioned in the talk that involves memorizing random person action object stories. But even these person action object stories are entirely characters, right? There's no numbers in you're not going to find many words with a number. So what I actually do is I have a file on Google Drive, and the file basically identifies for every site what my challenge is for that site. So, and it also identifies small modifications that I use to accommodate some of these rules. So, for example, it'll tell me that you appended a 1 to this password, or you appended an exclamation mark to the password. So, yes, that is a challenge that a lot of different sites have different requirements that about what they'll allow for a password. I would love to see a lot of these requirements kind of abolished, but given that every site kind of sets their own policy, I don't know how realistic that is. So, yeah, one can have simple tricks that you apply to accommodate these rules, but the scheme does require some external reminders of what you did to accommodate those rules. Yep. Okay.
That's it.
All right.
Thank you, Jeremy.